When I was first introduced to the complex numbers, I instantly fell in love with them. Or should I say, I was completely Mathsmerized by the ingenuity of Euler's idea, which was amazingly simple and yet yielded so profound results. So, still young and naive, in the pursuit of fame and glory, I set sail to explore new horizons in mathematics. My first attempted quest for new numbers started with the idea that what if I define logarithms for negative numbers? Now, initially I was so excited, but after little research, I discovered that logarithms for negative numbers doesn't yield new numbers, but rather complex numbers itself. So, I did not reap the fruits of my endeavor, but I did certainly enjoy the foray into the complex analysis. And today, I wish to share the thrill and fruition of my attempted quest with you. In this video, we'll explore how to find logarithms for negative numbers and, in general, how to find logarithms for complex numbers. Now, my basic assumption is you know a little bit about complex numbers. So now, having studied basics of complex number, we'll find out how to find log of a complex number. Now, if we have to find logarithm of a complex number, then the first thing that we need to do is we need to express complex number which is in the form x plus iota y in Euler's form, and for that we have to find its modulus, and there will be under root of x square plus y square, and we'll also have to find its argument which is theta, and that is tan inverse of y by x. So then I can express this number as r into e to the power iota theta. Now, there is one more thing about this logarithm function in complex number. So in real numbers or in real functions, so we have generally single valued functions. That is, for one value of x, there will be only one value of y. But in complex number, this logarithmic function, it's a multi-valued function. So for one value of z, we'll have many values of fz. So what we'll actually do is, rather than writing this complex number z as r into e to the power iota theta, we'll write z as r into e to the power iota 2n pi plus theta, where n belongs to set of integers. So if we write z as r into e to the power iota 2n pi plus theta, I can write this function fz as log r into e to the power I n 2n pi plus theta. Now log m into n, it is log m plus log n. So I'll simply write it as log r and then log e to the power iota 2n pi plus theta. Now another property of logarithms, so this power will come out, so I can write it as log r to the base e and then iota 2n pi plus theta and then into log e base e. Now same base, same number, logarithm is 1. So I can say the value of log z simply will be log r and then iota 2n pi plus theta, where n belongs to set of integers. So this is how we can find logarithms for complex numbers. Now we'll find logarithms for negative real numbers. Now here x is greater than 0, minus x will be negative. So I'll draw an argand plane and I'll represent minus x. Now first I need to find its modulus, which is nothing but its distance from origin. So r in this case simply will be mod of minus x, and there will be simply x. Now I'll find its argument. Now argument is nothing but the angle it makes with positive real axis. Now angle that any negative real numbers they'll make with positive real axis is simply pi. So in this case, this angle will be pi, and I know that this log, it's a multivalued function. So I'll simply write this angle as 2n pi plus pi, where n belongs to set of integers, or I can write, so this is 2n plus 1 into pi. So either I can use the formula directly now. So either I'll say this is log r, and r in this case is simply x, and then plus iota 2n pi plus theta, or we can go with the general proof, which is log x. I can write minus x as r into e to the power iota theta. So I'll write x into e to the power iota 2n plus 1 into pi. Now log m plus log n. So there will be log x log e to the power iota 2n plus 1 into pi. So I'll take this power out. So this is log x and then iota 2n plus 1 into pi. So again we'll get the same result, which is log of minus x will be log x minus iota 2n plus 1 into pi. Now say for example, I have to find the log of minus 1. So either I can use the direct result, which is log of minus x is simply log x plus iota 2n plus 1 into pi. Now in this case, the value of x is 1. So I'll write log of minus 1 as log 1 and then iota will be 2n plus 1 into pi. Now we know that log 1 is 0. So I can simply say log of minus 1 will be 2n plus 1 into pi into iota. So that is the value of log of minus 1. So we can find logarithm for any negative real numbers. Suppose the question is, we need to find log root 3 plus iota to the base e. Now first what I'll do is, I'll write this root 3 plus iota in Euler's form, and for that I'll need to find the value of its r and the value of its theta. So this root 3 plus iota, I can express it on Argand plane. So this is root 3 and this is 1. Now we can find the distance from origin, which is its modulus. So modulus in this case will be under root of 3 square plus 1 square. So r is under root of 3 square plus 1 square, and there will be under root of 4 and will be 2. So modulus of this complex number root 3 plus iota is 2. Now we'll find its argument. So we know that argument is nothing but angle it makes with positive real axis. So in this case, the value of tan theta will be 1 by root 3. So I'll write theta as pi by 6. Now since I know that this logarithmic function is a multi-valued function, so I'll actually write this theta as 2n pi plus pi by 6, where n belongs to set of integers. So I can write this complex number z, which is root 3 plus iota as r into e to the power iota theta. R in this case is 2, and then e to the power iota, and theta we have taken it as 2n pi plus pi by 6. Now I'll put this value of z in given logarithm. So this log root 3 plus iota will be log 2 into e to the power iota 2n pi plus pi by 6. So I'll write log 2 plus log e to the power iota 2n pi plus pi by 6. So now this power will come out and log e base e will be 1. So I'll simply write log 2 and then plus iota 2n pi plus pi by 6. So the value of log root 3 plus iota is log 2 to the base e minus iota 2n pi plus pi by 6, or we could have directly used the formula, and the formula was log z is simply log r plus iota 2n pi plus theta. So we can directly say, so this is log, and what's the value of r? R here is 2, so there will be ln 2 and then iota 2n pi plus theta. What's the value of theta here? Theta is pi by 6 for n belongs to any integers. So this is how we find logarithms for complex numbers. Now the second question, we are given the series expansion of log 1 minus x, and it is minus x square by 2 minus x cube by 3, and it goes on up to infinite when mod x is less than 1. The first question is, by choosing a particular value of x with mod x less than 1, show that log 2, it is 1 by 2 plus 1 by 2 into 2 square plus 1 by 3 into 2 cube up to infinite. Now in this, what we'll simply do is we'll let x as 1 by 2. So for this first one, we'll substitute x with 1 by 2. So it'll be this ln 1 minus 1 by 2 is 1 by 2. And here we'll get minus 1 by 2 minus 1 by 2 into 1 by 2 square minus 1 by 3 into 1 by 2 cube, and will continue. Now ln 1 by 2 is minus ln 2. So it'll be this minus ln 2, and that will be equal to minus 1 by 2 minus 1 upon 2 into 2 square minus 1 upon 3 into 2 cube, so on and so forth. Now we'll cancel this minus sign. We'll simply get log 2 equals 1 by 2 plus 1 by 2 into 2 square plus 1 by 3 into 2 cube, and which is what we need to prove in this first part. Now the second one is using part 1 and the fact that 1 upon n into 2 to the power n, it is less than 1 by 3 into 2 to the power n for n greater than or equal to 4. Find the integer k such that log 2 lies between k upon 24 and k plus 1 upon 24. Now basically all the terms in this series, they are positive. Now if you look at sum of first 3 terms, this sum will be this 1 by 2 plus 1 by 2 into 2 square plus 1 by 3 into 2 cube. Now this is 24, 12 plus 3 plus 1, 16 by 24. So this log 2 is sum of first 3 terms plus other positive terms. So we can write this log 2 will be greater than 16 by 24 and will be less than this 16 by 24 plus. Now from the fourth term onwards, we are given the condition that this 1 upon n 2 to the power n will be less than 1 by 3 2 to the power n. So if we substitute this, we write this as 1 by 3 and it will be 1 upon 2 to the power 4, 1 upon 2 to the power 5 up to infinite, which is nothing but an infinite GP. So if we simplify this right hand side, it will be the 16 by 24 plus 1 by 3, and this is A upon 1 minus R, and which is 1 by 2. So it is 17 by 24. So from here we can say value of log 2 will lie between 16 by 24 and 17 by 24. So basically value of k is 16. So for the second part, we get k as 16. Now for the third part, it says show that log 3 by 2 is 1 by 2 minus 1 upon 2 into 2 square plus 1 upon 3 into 2 cube. So for this, what we'll do is in the series of log 1 minus x, we'll simply put x as minus 1 by 2. So log 1 minus x will be log 3 by 2, and then it will be 1 by 2 minus 1 by 2 into 2 square plus 1 by 3 into 2 cube minus 1 by 4 into 2 to the power 4, so on and so forth. This is what we need to prove in this first part, and it says then deduce that log 3 is this value. Now we have already worked out series for ln 2, which is 1 by 2 plus 1 upon 2 into 2 square plus 1 upon 3 into 2 cube plus 1 upon 4 into 2 to the power 4. And if we add them, then we can write log m plus log n as log m into n. So it will be this log 3. If we add them, these terms, they'll cancel. So it will be this 2 times and then 1 by 2 plus 1 by 3 into 2 cube plus 1 by 5 into 2 to the power 5 up to infinite. Or we can simply write this as log 3 equals 1 plus 1 by 3 into 2 square plus 1 by 5 into 2 to the power 4, so on and so forth. This is your second part. Now we need to deduce that this value of log 3, it lies between 13 by 12 and 11 by 10. Now if we look at these first two terms, it is 1 plus and then 1 by 12. So there will be 13 by 12. And all other terms, they are positive terms in the series. So basically, this log 3 will be greater than sum of these first two terms, which is 13 by 12. And it will be less than 13 by 12 and plus. Now, as we have used in this question number 2, that 1 upon n into 2 to the power n, it is less than 1 upon 3 into 2 to the power n. Here we'll take 5 rather than 3. So we can write this as 1 by 5 and then 1 upon 2 to the power 4 plus 1 upon 2 to the power 6 up to infinite. If we simplify this right hand side, it will be 13 by 12 plus 1 by 5, and this is 1 by 16 and 1 by 4. So it will be this 13 by 12 plus 1 by 60. Now this is 65 plus 1, 66, which is 11 by 10. So from here we can write value of log 3 will lie between 13 by 12 and 11 by 10. Now in this fifth part we have to find which is larger, 3 to the power 17 or 4 to the power 13. Now we can write 3 to the power 17 as e to the power ln 3 to the power 17, or this is e to the power 17 ln 3, and the same way we can write 4 to the power 13 as e to the power 13 ln 4 or e to the power 26 ln 2. Now since exponential function, it is an increasing function. So basically we have to find out which of 17 log 3 and 26 log 2 is greater, and corresponding to it, that expression between 3 to the power 17 and 4 to the power 13 will be greater. Now first we look at this 17 log 3. Now we know that this value of log 3, it lies between 13 by 12 and 11 by 10. Now we multiply it with 17, we'll get this as 13 into 17 by 12 is less than 17 log 3 and will be less than 17 into 11 by 10. And if we look at log 2, we know that value of log 2, it lies between 16 by 24 and 17 by 24. Now we multiply everything with 26, we'll get this as 26 into 16 by 24. It'll be less than 26 log 2 and it'll be less than 17 into 26 by 24, which is 17 into 13 by 12. Now if we look at these two values, they're same. So from here we can clearly say 26 log 2 will be less than 17 log 3, or simply 2 to the power 26 is less than 3 to the power 17, or 4 to the power 13 is less than 3 to the power 17. So which is larger? 3 to the power 17 is larger. Next we have these limits, which are of the form limit x tends to a fx to the power gx. Now in this limit we have three standard indeterminate forms, and which are 1 to the power infinity, 0 to the power 0 or infinity to the power 0. Now in such questions, what we'll do is we'll write this as this limit x tends to a and then e to the power log fx to the power gx. Now we can take this power out, so it'll be this limit x tends to a e to the power gx into log fx. And since exponential function is a continuous function, we can take this limit inside, so it'll be e to the power and then this limit x tends to a gx into log fx. So in all the questions where we have function to the power function, we'll be writing it in this form. And we take an example. Say we have this limit x tends to 1 negative 1 minus x square to the power 1 upon log 1 minus x. Now this is 1 minus 1 0 and it is 1 upon log 0, which is infinite. So it is 0 to the power 0 form, which is an indeterminate form. Now we can write this limit as this limit x tends to 1 negative e to the power log 1 minus x squared to the power 1 upon log 1 minus x. Now we can take this power out, so it will be this limit x tends to 1 negative e to the power log 1 minus x square upon log 1 minus x. Now since this exponential function, it is continuous, we can take this limit to the power of e, so it will be this e to the power limit x tends to 1 negative log 1 minus x square upon log 1 minus x. Now we put x as 1, this is log 0 is minus infinite, and here also it is log 0 minus infinite, so it is infinity upon infinity form, for which we can use L'Hopital's rule. So it will be this e to the power limit x tends to 1 negative, and this is 1 upon 1 minus x square into minus 2x, and here it will be 1 upon 1 minus x into minus 1. Now here 1 minus x will cancel, so we can add this as e to the power this limit x tends to 1 negative, and this is 2x upon 1 plus x. Now if we put x as 1, it will be simply e to the power 1. So answer to this limit is e. Now here the question is we need to find this limit when x tends to 0. So this is L, and L be this limit x tends to 0 sin x to the power 1 by x, and plus this limit x tends to 0 1 by x to the power sin x. Now this is 0 to the power infinite form, and this is infinity to the power 0 form. Now basically 0 to the power infinite is not an indeterminate form. So we'll actually write this as e to the power limit x tends to 0 log sin x upon x, and plus this limit x tends to 0 e to the power limit x tends to 0 sin x, and this is log 1 by x. Now first we'll check its form. So this is log 0 is minus infinite, and minus infinite upon 0 is actually minus infinite. So this is e to the power minus infinite, and e to the power minus infinite is 0. So value of this first limit is 0. That means this L is simply the second limit, which is limit x tends to 0, and this is e to the power limit x tends to 0. We'll write this as minus log x upon cosec x, which is infinity upon infinity form. Now we use L'Hopital's rule, so it will be this e to the power limit x tends to 0, and this is minus 1 by x, and this is minus cosec x into cot x. Minus and minus will cancel, so it will be this e to the power limit x tends to 0, sin x into tan x upon x. Sin x upon x is 1 and tan x is 0. So it will be this e to the power 0. That means value of this limit is simply 1. And that's your option C. Now this second question is this limit x tends to 1 negative 1 plus cos inverse x to the power 1 minus x has the value which is the following. Now in this what we'll do is we'll let x as cos theta. Now when x is 1, theta is 0. So from here we can say this theta tends to 0 positive. So we can write this limit as limit theta tends to 0 positive 1 plus theta to the power 1 minus cos theta. Now this is 1 and here it is 0 to the power 0 form. Now we can write this as 1 plus e to the power limit theta tends to 0 1 minus cos theta into log theta, and we can write 1 minus cos theta as 2 sin square theta by 2 into log theta, which we can also write as 1 plus e to the power limit theta tends to 0, and this is 2 log theta upon cosec square theta. Now this is infinity upon infinity form. So if we use L'Hopital's, we can write this as 1 plus e to the power limit theta tends to 0, and this is 2 1 upon theta, and here it is this 2 cosec theta by 2, and then cosec theta is minus cosec theta by 2 and cot theta by 2 1 by 2. Now we can write this as 1 plus e to the power limit theta tends to 0, and this is minus 2 sin theta by 2 sin square theta by 2 tan theta by 2 upon theta, and we multiply and divide it with 2. This is 1 and sin 0 is 0. So this is 1 plus e to the power 0, which is 1 plus 1, and that is 2. So answer to this limit is simply 2. And that's your option B. Now here the question is, if e denote the base of natural logarithm, then the value of real number a for which the right hand limit x tends to 0 positive 1 minus x to the power 1 by x minus e to the power minus 1 upon x to the power a is equal to a non-zero real number. Now we'll solve this question using expansion. So we'll use the expansion of 1 minus x to the power 1 by x. Now one of the way to find this expansion is using Maclaurin series, which we have covered in one of the previous videos. Now since we are assuming it's for JEE, we are not going to use Maclaurin series in this case. So what I'll do is I'll say, suppose this expansion is y, and we can write this as e to the power log 1 minus x to the power 1 by x, which is e to the power 1 by x log 1 minus x. Now we'll use the expansion of log 1 minus x. So it will be this e to the power 1 by x, and it is minus x square upon 2 minus x cube upon 3, so on and so forth. So it will be this e to the power minus 1 minus 1 by 2x minus x square by 3. Now we'll take e to the power minus 1 common. We can write this as e to the power minus x by 2 minus x square by 3 up to infinite. Now this is expansion of e to the power minus x, and we know that expansion of e to the power minus x is 1 minus x, and x in this case is x by 2 plus x square by 3 and plus x square upon factorial 2. Now we are just concerned with first few powers. So in this case, if I take square of the series, then the term I'll get is x square
x square upon, now this is 4 into, will be this 8. So we'll get this as e to the power minus 1, 1 minus x by 2, and then it'll be this minus x square by 3 plus x square by 8. So it'll be this minus 5x square by 24. Now we use this expansion to solve this limit. Now we put this expansion in this limit. We can write this limit as limit x tends to 0 positive, and here it will be e to the power minus 1, 1 minus x by 2 minus 5x square by 24, and then minus e to the power minus 1 upon x to the power a. Now e to the power minus 1 will be cancelled. Now minimum power of x in the numerator is 1. So this limit will have a non-zero real number answer if the minimum power in the denominator is also 1. That means value of a must be 1 in this case. So the value of real number a, it must be 1. And if it is 1, then answer to this limit will be minus 1 upon 2e. Now in question number H, we are given a function which is y equals log 2, 9 minus 8 sin x minus 6 cos square x. And we have to find which of the following is the graph of this function in the range. Now in order to identify this graph, we'll change everything in sign. So we'll write this cos square x as 1 minus sin square x. So now this y, it will be log 9 minus 8 sin x minus 6 plus 6 sin square x to the base 2, or y equals log 3 minus 8 sin x plus 6 sin square x. Now basically it's a quadratic equation in sin x, and if we check its discriminant, it will be 64 minus 4 into 3 into 6, which is less than 0. So in this case, a is greater than 0 and d is less than 0. So that means this expression is always positive. So this function will be defined in this entire region. Now we'll find its critical points. dy by dx will be 1 upon ln 2 divided by 3 minus 8 sin x plus 6 sin square x, and here will be this minus 8 cos x plus 12 sin x into cos x. Now if we put it equals to 0, we get cos x, and here will be this minus 8 plus 12 sin x equals 0. Now cos x is 0, means x is pi by 2, and here we get sin x equals 8 by 12, which is 2 by 3. Now if we look at the graph of sine, its value will be 2 by 3 at 2 points. One of them is less than pi by 2, say alpha, and here this other point will be pi minus alpha. So we'll have 3 critical points: alpha, pi by 2, and then pi minus alpha. Now we look at the sign of dy by dx at x equal to 0. It will be this minus 8 and then positive value. So it will be negative. So here this value is minus, and then plus, and then minus, and then plus. So we'll have a minima at alpha and a minima at pi minus alpha, and we'll have a maxima at pi by 2. Now for this function, we'll find values of y at few points. So we'll find this value at alpha and pi minus alpha. So f alpha will be same as f pi minus alpha, because for both of them value of sine is 2 by 3. So it will be this 3 minus 8 into 2 by 3 plus 6 into 2 by 3 square log 1 by 3 to the base 2. Now we find value at pi by 2. This value will be 3, and then sin 90 is 1, so it will be minus 8 plus 6, which is log 1, and log 1 is 0. If we find value at 0, f0, it will be this log 3 base 2 and also be value at 2 pi. So this graph will start at a positive value and then it will decrease and it will take a negative minimum value. So this graph will start from positive value, it will decrease and then take a negative minimum value, and it will take a maximum value of 0 and then again a minimum negative value. And here we'll have one more critical point, cos x is 0 at 3 pi by 2 also. So we'll get another point which is 3 pi by 2, and at 3 pi by 2 again there will be a maxima, and we find the value at 3 pi by 2. At 3 pi by 2 sin x is minus 1, so it will be 3 plus 8 plus 6, and there will be log 17 base 2. So it will attain a maxima at 3 pi by 2 and then it will decrease to this value which is log 3 base 2 where we have started. So this first graph itself is the graph of the given function. This point here is pi by 2, this is 3 pi by 2, and this is alpha and pi minus alpha.
Let us take another example. So the function is ex into ln ex. Now the first thing, it's domain. So for logarithmic function, ex should be greater than 0, x should be greater than 0. So domain of this function will be x belongs to 0 to infinite. So this graph, it will be drawn from 0 to infinite. Now I cannot put minus x in that. So there is no symmetry in this given curve. In the interval 0 to infinite, both the function ex and ln ex, they are continuous and differentiable. So this function is continuous and differentiable in x belongs to 0 to infinite. Now the fourth step is to find the points where it will intersect x-axis or y-axis. I cannot put x as 0 because it is not included in the domain. So if I'll put y as 0, I'll get ex ln ex. So that means I'll get ex equals 1, x equals 1 upon e. So that means it will intersect x-axis at 1 upon e comma 0 and it will never intersect y-axis. Now fifth step is I'll differentiate the function. I'll find dy by dx. I'll put it equals to 0. I'll find critical points. I'll mark the point on a number line. Now when x is greater than 1 upon e square, 1 plus ln ex will be positive and before that it will be negative. So that means from 0 to 1 upon e square, it will be a decreasing function, and then after 1 upon e square, it will be an increasing function. Now at 1 upon e square, the sign changes from minus to plus. So that means 1 upon e square is actually a point of local minima. So I'll also find the value at 1 upon e square. So if I put x as 1 upon e square, I'll get minus 1 by e. Now again, I'll skip step 7. So I'll straight away go to my limits. Now here, because the domain is from 0 to infinite, I'll need to find this limit. Limit x tends to 0 positive ex into ln ex. So the first thing that we'll do in any limit is to find its form. Its form is 0 and ln 0 is minus infinite. So it is 0 into infinite, which is an indeterminate form. So I can write it as limit x tends to 0 positive. I can write it as e ln ex upon 1 upon x, which is infinity upon infinity form. Now I can use L'Hospital rule. So I'll differentiate numerator and denominator separately. So limit x tends to 0 positive. So it is e 1 upon ex and then into e, and this is minus 1 upon x square. So if I'll solve it, I'll get this limit as 0. So when x tends to 0, the limiting value of this function is 0. I'll also find limit at x equals infinite. So which is
ex into ln ex. Now when x tends to infinite, it is infinite, and log infinite is also infinite. So infinite into infinite is infinite, which is not an indeterminate form. That means the limiting value of this function when x tends to infinite is infinite itself. Now I'll start drawing the graph. So I've drawn the axis. Now first thing, domain is from 0 to infinite. So this graph will be drawn from 0 to infinite. There is no symmetry in the graph. So it will always be connected, and it's a smooth graph. It will intersect x-axis at 1 upon e. So I'll mark this point. Now I'll mark this critical point, which is 1 upon e square. So 1 upon e square, it will be before 1 upon e. So I'll mark this point as 1 upon e square. Now between 0 and 1 upon e square, it will be a decreasing function, and after 1 upon e square, it will be an increasing function. Now it has a local minima at 1 upon e square, and local minimum value will be minus 1 upon e. Now limiting value at 0 is 0. I'll put an open circle at 0, and then I'll start drawing the graph. So between 0 and 1 upon e square, it will decrease, and it will have a minima at 1 upon e square. It will pass through 1 upon e, and then it will go up to infinite. So that is the graph of ex ln ex.
Now question number 2 is, we need to prove that this integral from 0 to pi by 2 log 1 minus x square cos square theta d theta is pi log 1 plus under root 1 minus x square minus log 2, where x square is less than or equal to 1. Now variable of integration is theta. When we'll solve this integral, we'll get this as some function of x. So we'll write this as fx. So fx equals this integral. Now here we'll also work out its initial value. When the value of x is 0, this value will be log 1, and log 1 is 0. So when the value of x is 0, value of this function is also 0. Now what we'll do is, we'll differentiate this function with respect to x. Now again we'll use Leibniz rule. Now we have to differentiate this function partially with respect to x. Now if we differentiate this function partially with respect to x, we'll write this as 1 upon 1 minus x square cos square theta into minus 2x cos square theta d theta. Now what we'll do is, we'll multiply it with x, and we'll divide it with x, and then we'll add 2 and subtract 2. So we can write this function f dash x as 1 by x, this integral from 0 to pi by 2. Now here we'll take 2 common, and it'll be 1 minus x square cos square theta minus 2 upon 1 minus x square cos square theta d theta. Now we'll split this integral in 2 parts. So we'll write f dash x equals 1 by x from 0 to pi by 2, 2 d theta, and then minus 2 by x from 0 to pi by 2 d theta upon 1 minus x square cos square theta. So we can write this f dash x as 2 by x, and then value of this integral will be pi by 2, and then minus 2 by x from 0 to pi by 2, and again for this we'll divide everything with cos square theta. So in the numerator we'll have secant square theta d theta upon, now this is secant square theta minus x square, and secant square theta is 1 plus tan square theta. So we can write this as 1 minus x square plus tan square theta. Now here 2 and 2 will cancel. So we can write this f dash x as pi upon x minus 2 upon x, and here we'll take tan theta as t, then secant square theta d theta will be simply dt. So we'll get this integral as dt upon 1 minus x square plus t square. Now when theta is 0, t is 0, and when theta is pi by 2, t is infinite. This is of the form a square plus t square. So we can write this as f dash x equals pi by x minus 2 by x, and here will be 1 upon a, and a in this case is under root of 1 minus x square tan inverse t by a, which is under root of 1 minus x square from 0 to infinite. So we can write this as f dash x equals pi by x minus 2 by x under root 1 minus x square, and here we will put t as infinite, tan inverse infinite is pi by 2, minus tan inverse 0 is 0. Now here 2 and 2 will cancel, so we can write f dash x as pi by x minus pi upon x under root 1 minus x square. Now we integrate this function with respect to x. On the left hand side, it will be simply fx. This one will be pi log x, and then minus, we'll take this pi common, and it will be dx upon x into under root of 1 minus x square. Now this is of the form linear into root quadratic, and when it is of the form linear into root quadratic, we'll take this linear as 1 upon z. So we write dx as minus 1 upon z square. So this function fx will be pi log x minus pi, and then we write dx as minus 1 upon z square dz upon 1 upon z under root of z square minus 1 upon z. Here z and z will cancel, so we can write this fx as pi log x plus pi dz upon under root of z square minus 1. Now this is fx equals pi log x plus pi, and then it is log z plus under root of z square minus 1, and then plus c. Now we'll take pi common, and log m plus log n is log m into n. So we can write this as fx equals pi, and then log xz plus under root of x square z square minus x square plus c. Now x into z is 1, so we can write this function fx as pi log 1 plus under root of 1 minus x square plus c. Now we already know that when x is 0, value of function is 0. So we'll put x as 0, we'll get this as pi log 2 plus c. So value of c is minus pi log 2. So we can write this function fx as pi, and then log 1 plus under root of 1 minus x square minus log 2, and this is the result that we need. Pi log 1 plus under root 1 minus x square minus log 2.